Algebra 1 students, welcome to your 4.2 notes, patterns, and linear functions. We're going to start with a lot of terminology, and then we're going to look at some relationships and some patterns that we find in some various situations. Definitely an interesting day. I think it's one that you can pick up on, but you'll want to pay attention closely. All right, so let's get started here. Patterns and linear functions. First, some terminology. These words are all pretty important. A dependent variable is a variable whose value depends on that of another variable. When we're talking about linear equations, usually we use y to represent the dependent variable. Independent variables are variables whose value does not depend on that of another variable. That's usually x when we're talking about linear equations. The input represents the independent variable, the term that you're choosing to plug in. The output is your y value or your dependent variable. Okay, a function is a relationship that pairs one input value with exactly one output value. So whatever input value you plug in, you get something out. It's not possible to plug in one number and get two results. Like I can't plug in 3 and find that the answer is 7 or -2. That doesn't happen. It's one or the other. All right, and a linear function is a function whose graph is a non-vertical line or part of a non-vertical line. So a linear function, as the name would suggest, is a graph that looks like a line. So let's take a look at an example, and we'll use some of the terminology throughout this. But for the diagram given, find the relationship between the number of shapes and the perimeter of the figure. Notice that I tweaked the instructions just a little bit. There were some extra unnecessary words in yours. Represent this relationship using a table, words, an equation, and a graph. So we're going crazy here. We're going to use lots of methods. All right, so let's do this. Let's start filling in what we know. If we have one triangle, you can see that example over here. The perimeter is exactly 3. When we have two triangles, you can see the perimeter is 4. This next one, we have 3 triangles, and the perimeter is 5. And then the last one, 4 triangles, perimeter 6. Now here's what I would suggest. Let's continue with this pattern and see what we would find. One would be to go to 5 triangles, we know it would be 7. 6 triangles, we know it would be 8. Now if it was n triangles, where we're just saying it's an unknown number of sides, essentially what I would do is look at, well, what's happening here from 1 to 3, 2 to 4. We're always adding 2 to the number of triangles. All right, one more thing to possibly consider here. What if we had 0 triangles? I know it doesn't necessarily fit with reality, like what's the perimeter of 0 triangles? Well, 0. But consider it just as a linear pattern and don't think of it in terms of triangles. You can see that as you move back up this chart from 2 to 1, you go down 1. From 1 to 0, we can assume we would move down 1 as well. The reason I'm doing that is because that helps me with the plotting of points. 0, 2, 1, 3. And this pattern would continue. There's 4, 6. Now the ones that we made the assumptions on, and we could draw them out and figure it out, would be like 5, 7, 6, 8. You could continue on as far as you want here. That graph ends there, but the graph looks something like that. Now they said to put this in words. So what we would say is something like the perimeter is 2 more than the number of triangles. Okay, and the equation, well, when you look at this graph, you can see our slope is up 1 and right 1. So our equation would be y equals 1 times x, or just simply x, but notice the y-intercept is at 2. So y equals x plus 2. So we're taking data, doing a little analysis, kind of interesting stuff. All right, let's go on to the next one and see what it looks like. Okay, so this time we have squares that are forming T's or crosses, whichever way you want to think about that. And we're going to do some similar things. We want to find the relationship, and we're going to write it as a mathematical equation between the number of the figure number and the number of squares in the figure. So what I'm going to do is I'm going to say that's figure number 1, that's number 2, that's number 3, and this last number here is the 4th. Okay? And then S is going to represent the number of squares. So even though we don't have the chart like we did on the last one, we're going to do the same thing, and we're going to figure out how these values are connected. So the number of the figure, we numbered them 1, 2, 3, and 4. The first figure had just 1 square. The second, you can count these, but there are 5 there. The next one has 9, and then the next one has 13. That's the 4th one. Now here's a question you could think about. What if you had, say, just n, figure n, where you don't know if it's number 5 or number 72? How could you figure that out? Well, that's what we kind of have to look at and see here. And what I would suggest is, you're increasing by 4, so that tells us then our relationship is number of squares is going to be 4 times n. But notice there's a little issue here. The first figure doesn't have 4 squares, it only has 1. The second one doesn't have 8, it has 5. So what we need to do is make a little adjustment and make it minus 3. Now some of you may think of it more like this. It's 4 for each additional side. So we could do n minus 1, or each additional figure beyond the first. And then you would do something like that, and then you would add 1 because the first one does have exactly 1. Now if you simplified this, these two equations would be identical. And actually, we just answered this question right here. N would be 4n minus 3. Alright, let's keep going. And I left a blank one there for you on purpose so you could flip to the next side. Alright, so for each table, determine whether the relationship is linear, and then represent the relationship using words, an equation, and a graph. Now I'll tell you this, the first thing I look at, if it says it's linear, I look at change. 1 to 3, that's plus 2. 3 to 5, that's plus 2. And 5 to 7, that's plus 2. That's a pretty strong hint. We do have to make sure that our x change is also constant and it's counting by ones, so we've got that. So I know this is linear already, just based on change. Now let's do it visually. Let's plot these points. 0, 1, 1, 3, 2, 5, 3, 7. So this would be the other way to look at this, is just to go ahead and plot those points, and you can see that there's a line that would connect those. I'm kind of missing here. This is what happens when you draw by hand. But there's a line that connects those points, just like that. So we absolutely know this is indeed linear. Okay, so we need to come up with the equation. Sometimes it's nice to come up with an equation when we have the line already right there in front of us. We can see that the slope is up 2 and right 1, so we're going to say y equals 2x. The y-intercept would give us plus 1. Now the way I wrote this in words is something like this. The graph started at 1, and moves up 2, for each step of, or I should say each step in the x direction. Alright, that's a little shaky. I'm not sure I like how I wrote that in words, but it works. Some of you might just write it in terms of what's the slope and what's the y-intercept. I would understand that as well. Alright, why don't you do this? Why don't you go ahead and pause the video. Give this next one a shot. Something I want to point out to you is notice that there are missing terms between 1 and 3 and 4 and 6. That doesn't mean they couldn't be there, but don't assume it's not linear just because those are missing. So pause the video, give this one a shot, and then compare your work to. All right, welcome back. You can see what I've done here. I've shown that this is indeed linear. You can kind of extrapolate, I suppose is the word, what other values besides just those four would be. We know that it's a linear equation. You can see that here. I've got the equation as being y equals x minus 1. You have to kind of envision that line moving further to the left to find that y-intercept. Knowing that the slope was up 1, right 1, you could go down 1 and left 1, and there's your y-intercept right there. And then the slope, of course, is 1. So y equals x minus 1, and I just, in words, described it that way. There are plenty of other ways you could use words to describe that, but I felt like that was as good as anything, so I went with it. All right, last one. Basically the same instructions. Here's what I would look at. We have constant change in the number of cans of pop. The other thing I noticed is we have constant change in cost. Each one of these steps is an additional $1.29. So when we graph this, 1 and 31.97, and there's just a little approximation going on here. So I've got my 4 points plotted now, and I'm going to look at describing this in terms of an equation and also in terms of words. Now you'll note that I went ahead and included a point that wasn't here. That was the point 0, and I'm going to write it down right over here, and $30.68. This was the point before the one here by subtracting $1.29. That helps me because it gives me the y-intercept. So y is going to be $1.29x plus 30.68. All right, so in words, I would just do something to say that we are paying $30.68 plus $1.29 per can of pop. Not a great deal, definitely not a great deal, but it is the deal that's here on this problem. All right, folks, it's definitely kind of a different lesson. I hope this works well for you. Come ready to work and bring your questions to me. You guys have a spectacular day.